Okay, let's officially start this lecture. So I'm Alejandro Aragon, and I will be teaching you advanced finite element methods, which is Mechanical Engineering 46050, as you may know already. In this class, we're going to learn finite element analysis, and a lot of what we're going to do is actually convergence analysis. Convergence, by that I mean that we are going to try to solve a problem, and we're going to use different discretizations, right? So a coarser to a finer scale. So this picture, in essence, captures more or less what we're going to try to do. So this is an artist, actually. This is actually a real sculpture from a Spanish artist called Rómulo Celdrán, and it captures in a way what the essence of this course, right? We're going to try to improve the finite element approximation by increasingly refining our meshes, right? So he comes from an optics perspective, right? So you see all these pixelized nuts. But we do that in also from mechanics, right? We're going to reduce the mesh size, and then while doing so, we expect that the finite element solution is going to get better and better. And that is essentially the basis from what we call the H version of the finite element method. So H, we define as H the element size of our discretization, okay? Okay, so regarding the contents of the course, we are going to look at everything from the very basic. So if you never took a finite element course, it's good news that we're going to start from a 1D bar, the same way we did it for the nonlinear mechanics. So if you attended nonlinear mechanics, then you do have already a basis for what we are going to see. Now, of course, the lecture in nonlinear mechanics is going to just be the first two lectures here. So we are going to expand that. We're going to explain more in detail. But of course, we are going in this class, we're going to go way beyond that, all right? So we start with the linear elastostatics problem of a one-dimensional bar, right? And then we do everything that there is to be done from deriving the governing equilibrium equation, right, to the discretization process, right? We do the Galerkin projection. We obtain the final element discrete equations, and then we're going to solve that. And we're going to look at some more theoretical aspects of the finite element method. We look at the orthogonality of the Galerkin error. We see how incredible that Galerkin projection is, what it does. And then we are going to look at the isoparametric mapping. So if you grab any software today that does finite element analysis, the chances are that it is doing something called isoparametric analysis, meaning that the geometry is expressed or approximated in a way that is exactly the same way the finite element field is approximated. Okay, if those have the same nature, so if they are approximated the same way with the same polynomial interpolation, the formulation is called isoparametric. Okay, so we will do that as well. We will understand that, and then of course everything that we do in 1D, similarly to what we did in nonlinear mechanics, it can be nicely extended to higher dimensions, and so all the insight that we gain in the 1D case, we can get exactly the same insight in 3D. So there are some subtleties here and there. Formulations get a little bit more complicated because now we're dealing with tensors instead of scalar fields, right? And so it's a little bit more complicated, but most of what we gain for the one-dimensional case is going to help us understand the higher dimensional case, all right? And we do the same. We go to the strong form of the boundary value problem, the weak formulation, the Galerkin projection, all the way up to determining the discrete equations, all right? After that, we will delve into the world of higher order interpolations in the so-called P version of the finite element methods. Remember, first we're going to look at the H version of FEM, where we improve the discretization by reducing the size of the finite elements, right? And now we're going to look at the P version of the finite element method, where the basis is, well, I want to keep my mesh fixed, and I want to improve the approximation by just increasing the interpolant, the order of the interpolant that I'm using. So that is the P version of FEM. And so we look at these hierarchical shake functions. So basically, we take the linear approximation of standard HFEM, and then we add a quadratic function on top, and then a cubic, and then a quartic, and then a quintic, and so on. And by doing so, you would expect that this is going to behave better. And as you will see in this course, and if you manage to finish the course and do the project, you will see that PFEM is an incredible method. And for smooth problems, it actually outperforms the H version of FEM. Okay. So you have. So we're going to do a comparison. We're going to have some theoretical results on those two different approaches: H version of FEM, P version of FEM. And actually, you can combine both, right? So you can think of a method that is called the HP extension, right? Where you can improve the approximation by doing both. You refine your mesh size and you increase the polynomial interpolation order, right? And this is actually very, very powerful, right? And it has proven to be very effective for solving problems with singularities. And so what is a problem with a singularity? Well, it's a problem where at some point your field just explodes to infinity, and so there are problems like that. And we will also categorize those problems, right? And along the way, we are going to look at implementation details. So I will give you a finite element code in Python, right? You're going to be modifying this code to solve the two problems that we have for the project. And those of you who finalize the project are going to learn truly what finite element analysis is, okay? And since my objective is for all of you to learn finite elements, that is my primary goal, I don't have deadlines. So you can come 2 years from now and say, hey, Alejandro, here, this is my report. And I will grade it for you, and you will have your grade. So this is a bit dangerous because, yeah, some people wait 2 years or they never do it, right? But I cannot push a deadline to you because you all come from different backgrounds, right? Who knows how to program in Python, for instance? Who has never written a line in Python? Yeah, so you see, there is such a big disparity. Those of you who never wrote a line in Python are going to try to spend a little bit more effort trying to catch up, learn the language. For that, I am giving a Python crash course this coming Friday. So I'll talk a little bit about that. So register if you never did anything in Python. So I'll give you this code, and the idea is, okay, I'm going to change the code. I need to understand first how the code works. It's a very small piece of code, and yet it can solve 1D, 2D, and 3-dimensional problems. It's very, very small, very compact. So obviously, the code has not been written for performance, but for readability. So it's a very straightforward to understand. And then, well, once you understand the code, you're going to be changing it so that you can implement whatever needs to be implemented to solve the project. Okay? All right. So these are the course objectives. Derive the finite element discrete equation starting from the equilibrium equation or any other elliptic partial differential equation. Actually, whatever we do can be nicely applied to other elliptic boundary value problems like heat conductions, for instance. Of course, we're not going to look at the more advanced finite element formulation. So you have elliptic problems that are the easiest, right? You have parabolic, you have hyperbolic problems. And there are methods that are better suited for hyperbolic problems, for instance, right? Like a discontinuous Galerkin move. So we are not going to delve into those. So we are going to, as an objective, identify the limitations of FEM and understand the means to overcome them, right? So one of the nice tools that you will get from this class is that you're going to be given a problem and you're going to understand what needs to be done to get an appropriate solution. Okay, this is the way if you heard in nonlinear mechanics, I was telling everybody, right, like a way to sell this course. When you are given a problem, you need to analyze something. You can put it in a computer, and the computer is going to tell you a result. It's going to give you something. How do you know whether it is any good, right? So in this course, you're going to get those tools. You're going to understand that there is a way to see whether your solution is good, even if you don't have an exact solution for that problem. Actually, most problems don't have an exact solution. And so we have to find the means to understand whether what we get from the computer makes any sense, right? So this course is going to give you those tools. Evaluate the performance of the method on academic problems. And yeah, of course, the project, the objective of the project is for you to understand the methods and how they perform. And so for that, I'm not going to give you a very complicated analysis of a mechanical part that you would probably encounter in the industry, but rather problems that are academic, so you can really understand how these methods work. And then we'll extend the software package provided to simulate complex problems, and I already discussed about that.
The solutions of the problem that you provide, are they exact? So is there a way to
Yes.
analytically?
That is why we're going to focus on academic problems, because you have an exact solution and you can use the exact solution to understand how well you're doing. Yeah? But that being said, you are going to still use these other tools. So you're going to imagine, okay, there is no exact solution. Now I'm going to apply this a posteriori error analysis. And so we are going to try to estimate the exact value of the strain energy. Even if we think that there is no exact solution, we can estimate an approximation of the exact strain energy that we can use to see our convergence. Okay? All right, so the material is based on our book. It's called Fundamentals of Enriched Finite Element Methods. And of course, the book goes way beyond what you're going to see in this class. Actually, this class was a prerequisite for my next class that is called Enriched Finite Element Methods. But for the time being, I have stopped the class. And the reason is that, well, I already told you the bad news, right? Half of you are going to not make it, right? Based on statistics. So from the half who makes it, right, only 1/4 take my next course. So in the end, I was teaching in the past to just a handful of people. And so I decided to change that to a more graded, like a PhD level. And so now I'm teaching this as a part of a graduate school course in the whole Netherlands. So for the time being, this is not happening, but I strongly recommend that you download the book. It's for free for you, so you can download it, and it's a nice resource. Of course, I'm not saying this is the only one, and I list here 2 of my favorite books. You have an incredible book by Savon, Babuška. Babuška is really one of the gods of finite element analysis. He's no longer with us, unfortunately, but he was really one of the people in the field of computational mechanics who pushed finite element technology to the limit. He came up with so many brilliant ideas. And then you have Tom Hughes. The second book is by Tom Hughes, and he's still alive, right? He's really perhaps the main person leading the finite element world right now, and he's behind this so-called isogeometric analysis. Who has heard that term? Isogeometric analysis. No, so the idea is that you can basically do finite element analysis on your CAD, on your computer aided design, right? So you can use the so-called NURBS as basis functions to do the analysis as well. So the idea is, okay, now we shortcut, because from the CAD we don't need to create a finite element mesh that looks like a CAD. We can just use the CAD, right? So that is basically the idea behind isogeometric analysis, and he has been pushing this technology for a few years. I am not one of those guys who jumped into that wagon. I stayed with standard finite elements, but lots of people are using that, okay? So again, the contents of this course are going to be chapters 2 and 3 from my book. So you can download it for free. Yeah?
Yeah, sorry again for another question.
No problem.
How geometric is this course? Because
How you what?
geometric is this course? Because
How geometric?
yeah, because when you're doing finite element method,
Yeah.
it's always talking about some sort of a shape that forms
Yeah.
some sort of a physical phenomena transporting through material.
Yeah.
Is it because it's so, to me it's always some sort of a relationship between some sort of a geometry and then some sort of a analytical solution.
Yeah.
That's discretized.
Yeah. Yeah.
How much of that, that jump between the geometry to the analytical solution is part of your...
Well, the problems that we will see and the problems in the project are not really that complicated geometrically speaking. So they are not very hard to create, the meshes, okay? Remember, the idea is that you have an understanding on the methods, and for that we don't really need to have complicated geometries. And in fact, remember that for complicated geometries, there are no exact solutions. Okay, so normally exact solutions only exist for problems that are very simple, right? A hole in an infinite medium, for instance. Yeah. Okay. We will be using the Nota Bene. Nota Bene is a system, right, developed by MIT, and it's really a great tool that I've been using already for many years. And the idea of the Nota Bene is like, okay, you have the the lectures, right? The book material, and so whenever we are not facing each other, we can still interact through the system, all right? So you read something in the book chapter, and it's like, okay, I don't understand this. Okay, you can ask questions, and you could also reply to your own peers, or if I see that no one is replying, I jump in and I explain something. So if something is not clear, you make your comment, right? You can annotate. It's a really a nice tool to interact outside the class, all right? And again, we will be posting the lectures in Brightspace. There is also going to be a lot of course material in the Brightspace. I'll give you the final element code. I'm going to post it there as well. So make sure you register. By the way, I forgot to mention, but nota bene, some of you already sent me your registration, right? So you have to go to the Nota Bene website. So read the announcement. You have to go to the Nota Bene, register, and send me your registration. So whenever you send me that, I add you to the course, and then you are seeing the course in your list. Okay. Well, Brightspace, we're going to put the lectures there, some other material, the LaTeX file, the template that I use also for the class is also going to be there. So that's it for the Brightspace. The assessment, as I said, is going to be a project that is going to be graded. It's 100% of the grade, right? And I'm very particular about grades, right? If I give you a project and you do everything right, I give you a 10. You can have a 10 for this class. Actually, many people get a 10 for this class. Remember, I told you, only half of you will make it, right? Well, if you make it, and you make everything right, you get a 10. That's a nice incentive, right? If you have a weak GPA, you can use this class to improve your GPA. Now, of course, getting a 10, yeah, you have to do everything right. That's going to be a bit hard. But again, if you put the hours, if you put the enthusiasm, and you put what it takes, you get your hands dirty and you understand how this works, then you get a 10 for this class. Okay. For the project, of course, I ask everybody to do this individually, right? It doesn't really make sense to work with other people. Remember, my objective is for you to learn the content. So you can talk with your peers. You can, let's say, you can discuss. That's nice because you get to a synergic interaction. But the moment you are sharing code, that's it. You went too far. Okay, so don't share code. Otherwise, I mean, I can control that, right? I have this tool that tells me, well, this code looks suspiciously similar to this other code that was submitted earlier. But why? Again, you are adults at this stage. You are your own masters. So if you really want to learn this, you have to do this on your own, okay? Prior knowledge, I said that there is not going to be any requirement for prior knowledge. We are going to start the content from the one-dimensional bar, which is the simplest mechanical system you can think of. And so regarding Python, I see that people have different backgrounds here. And that is the reason also why I cannot assign deadlines, right? Remember, for those of you who just arrived, I will give a Python crash course this coming Friday. And the idea is not that you become experts, right? But at least you have some understanding about what Python does. And if you program in a different language, that you understand also what are the differences. Yeah?
When it comes to code, how are external sources regarded? So for example, Stack Overflow, some people write code with ChatGPT, which is based on physical resources.
Yeah, so ChatGPT, we have to address the elephant in the room, right? Everybody's using ChatGPT nowadays. Yeah. Now try to put the project and ask ChatGPT to solve the assignment for this class. Yeah, of course it's not going to do it.
Right, it won't work like that.
Yeah.
I use it as a tool, for example, to write certain types of structures.
Yeah, of course, the more ChatGPT you use, the least your understanding of what you're doing. So keeping that in mind, I'm not going to prevent you from using ChatGPT. Look, we recently developed this application, right, for the Vision Pro. Yeah. So we can do design of topology optimization in augmented reality. Right, super cool. I had no clue about Swift. So I was asking ChatGPT, how do I do this in Swift? So we ended up creating this application, and ChatGPT helps us a lot. So it's really a valuable tool. I mean, it's like whenever the calculator was invented, no one did hand calculations anymore, right? So you know, I cannot prevent you from using ChatGPT, but mind your use of it, right? Because remember, the idea is that you really understand the concepts of this class, right? So if you get to a stage where you finish this course and then you don't understand the code that is written, then you probably went too far in terms of using ChatGPT, all right?
And then I have
Yeah.
like, and Stack Overflow, which is because ChatGPT there's no real like
Yeah.
copyright on stuff, and Stack Overflow does.
Yeah.
It's a resource basically with an author.
Yeah.
How do we treat that?
Oh, I love Stack Overflow.
Yeah.
It's an incredible resource for programmers. Like, obviously, we have different expertise when it comes to programming, and so if you cannot find the answer that you're looking for on the internet, yeah, just post a comment on Stack Overflow. Then you're gonna have an understanding. Of course, this is the same. You can get the same answer by ChatGPT, right? It's basically expert knowledge. Now, mind ChatGPT, because ChatGPT is very good at some things, right? But it is bad at many others. So be careful with ChatGPT, right? I was doing a literature review, for instance, and I was like, okay, give me because I know my field, right? So I was asking, so who are give me a few papers that deal with this and that, whatever, all over the place. And it makes sense because ChatGPT is a predictive, it's like it's one of these, it's based on a diffusion model, right? These foundation models that are supposed to be very good at extrapolating, right? Creating new content, right? So it's like generative machine learning. And so it's very good at creating new stuff, but it is not very factual. So be careful with ChatGPT, all right? So on Wednesdays, so I will be the one giving you the theory, but on Wednesday we're gonna have Paul, my PhD student. He's going to be working with you on more practical aspects. So he's going to go through some of the examples of the book so that you have understanding. And the both of us, hopefully, we will complement each other in such a way that you get the theory from me and the more practical aspects from him, okay? All right. I think that's it for this introduction. Questions? Yeah.
How will that Wednesday session be compared to last year's? Because last year's you basically went through quite a lot of practice, and
Yeah.
You showed quite a lot of Python, and if anyone had any questions regarding that, you could ask them during that session.
Yeah.
But now you're saying that the Wednesday session will be an actual working lecture where your PhD student will go through more details and
Yeah.
clarify if anything.
Yeah, so he will be essentially doing what I was doing last year. So I'm getting a bit of help this year from him. So it's essentially the same. He can go through the code and talk to you if you don't understand something. And also I want him to look and go through some of the examples that I lay down in the book, right? So that you also look at that material. Yeah. Any last question? Yeah.
When are we going to be able to start with the project?
Oh, very soon. Very soon. More questions? Okay.